Hi, this is Miss Kaiser.
This is Miss Mochizuki.
And Miss Mick.
And we're going to go through lesson 10.6 for you. Segments and circles. So get out your note packet for today. And today is Thursday or Friday.
Yes.
All right.
Okay, we are going to be talking about different relationships between segments that can be drawn in and around circles. And the first types we're just going to look at are segments of chords. And so when you look at that picture down below, you can see that there are two chords drawn. They intersect at point E. The theorem about the segments of chords says that if they intersect in the middle of a circle, and not the middle, but the interior somewhere, anywhere inside, then the product of the lengths of the segments of one chord is equal to the product of the lengths of the segments of the other chord. In other words, if you take the two pieces into which DC is divided, which are EC and ED, and you multiply those together, and you take the two segments into which CD are divided, or AE rather, and you'll get AEA times EB, those are going to end up being equal to each other. And so we can practice with a few problems on the next page.
Awesome. So Miss Mick's going to start us out here. So what we're doing is we're finding the length of each segment. But before we do that, we need to find what the value of x. So Miss Mick's going to give us the equation for the value of x.
Okay, so we have segment BA is split into two parts, x and the quantity x plus 6. So we need to multiply those two parts of the segment together, x times the quantity x plus 6. Make sure you're writing parentheses around x plus 6. And that's going to be equal to the product of QP's segments x plus 1 and x plus 4. So we see we're multiplying two binomials on the left, so you can use your box method, FOIL method, distributive method, whatever you feel comfortable using, but we need to multiply those two binomials and making sure that we remember those linear terms, what we sometimes call those middle terms. And on the right side of the equation, we're just using the distributive property to make sure that x gets multiplied times the x in the parentheses and the 6.
And then on the left side of the equation, we're foiling it out. So when we multiply x and x, we get x squared. And then when we go outer and inner, we get 4x plus 1x, and that adds up to 5x. And then we multiply 1 times 4, and that adds up to 4.
The next step in this equation is that you want to combine your like terms. And the cool thing about this one is that they both have an x squared. And so if you just subtract x squared from both sides, it is eliminated from the problem, okay? Because you're going to get 0x squared. So we end up with just a nice move to the next line. So now that we have eliminated the x squares, we have a simple linear equation that I think you can solve. All you have to do is subtract 5x from both sides, and you get x equals 4.
Alrighty, so then the next thing to do is to figure out what each segment equals. So we want to figure out what BN equals, what NA equals, what QN equals, and what NP equals. So I'm going to plug that in over here. And so then it's just simply adding together. So BN is 4, and then NA is 4 plus 6, which is 10. So if you add those two numbers together, you get AB. Mm-hmm. And so AB turns out to be 14. And then for BQ, you just got to add QN and NP. So you're going to add 5 plus 8, which is 13. Okay?
Sounds great to me.
That's good.
All right, let's move on. All right, in the next equation, Mick, can you take that away and explain that to them?
Sure, so we have two segments, and one of them is 9 and 2. So we're going to find the product of 9 and 2, write that on the left side of the equation. And we have another segment that's 6 and x, multiply those together. When we simplify, we get 18 equals 6x, find that x is 3.
Awesome, so that was pretty simple. For the next one, go ahead, Miss.
Okay, for the next one, we're going to do the same process. We multiply along each one of those segments. So on one side, we're going to have 6 times 5, and on the other side, we're going to have x times x plus 1. So we have to distribute on the left to get x squared plus x, and multiply on the right to get 30. Well, this is a quadratic equation. Whenever you have a quadratic equation, you have to have 0 on one side in order to solve it. So we're going to move the 30 to the left side.
And
Okay.
so this is a factorable quadratic. So some quadratics we're able to factor and some we're not. This one we're able to factor. So the way to factor this, if you remember, we've had lots of practice factoring last chapter. So it's two numbers that multiply to negative 30 and add up to positive 1. And since it's going to add to positive, multiply to a negative, one number needs to be positive, one number needs to be negative, and the larger one is positive. So what two numbers are those, Moch?
Well, it looks like 6 and negative 5 will work. So we have x plus 6 and x minus 5 equals 0. Now, in order for this equation to be true, either one of those expressions has to be equal to 0. And so you know from the first expression that x could be negative 6, and from the second, x could be 5. So we write down x equals negative 6 and x equals 5. Then we think about it. X can't be negative 6, it's a length, okay? So it's an answer that we found legitimately doing the algebra, but it doesn't work for our geometric problem. So we call that an extraneous solution, a solution that's found that just doesn't work in your problem. And so the correct answer is x equals 5.
Awesome. Okay. So let's move on. So this page of notes is just talking about a secant and a tangent. And when you have a secant, you have an external portion of the secant, and then you have the entire secant. And when you have a tangent, the external portion equals the entire thing. And this is important for our next theorem. In our next theorem, Moch is going to take this away because she's good at explaining these theorems.
Okay. If you have two secant segments and they share the same endpoint outside the circle, then the product along the line of the external secant segment and the entire secant is going to be the same in both directions. So EA times EB, the external segment, times the entire segment, is going to equal the external segment on the bottom secant, EC, times the whole secant, ED.
Awesome. Okay. So in both of these problems, there are two secants. And so when you look at A, RP is the external, which is 3. And then the entire segment is RQ, which is 3 plus 9, which is 12. And then RS is the external segment, which is 4. And then RT is 4 plus X. So you're going to take the product of each of those, as you can see. So next you're going to multiply 12 times 3, and you're going to distribute your 4 on the other side. And then, I know this went fast, but I know you guys know how to solve that linear equation. So we went through and solved for X. Hopefully you didn't have any difficulty. So let's look at the next problem. Mick, can you give us the equation for the next problem?
Sure, we're going to have the external portion Z times the quantity Z plus 12 is equal to the external portion 4 times the quantity 4 plus 8. We can just write that as 12.
Great.
Okay, now we need to solve this equation. And unfortunately, this is not going to be a really easy one, so you're going to have to concentrate on this one. We distribute and multiply and set it equal to 0, like we do whenever we run into a quadratic equation. However, you could sit there and think, what two numbers multiply together to give me negative 48 and add up to 12? But you're going to be thinking all day long. You know why? Because it just doesn't work. There isn't a good one. So Miss Kaiser's going to take away what you can do instead.
Right. So we gave you a worksheet to work on, and there was a couple examples on it. And I think that was on Monday's assignment. We gave you a worksheet that was completing the square worksheet. And it had some examples on the top, and then you were expected to do the problems. And then there was an answer key there. And it was on completing the square. So I'm going to use that method for this problem. hopefully you understood it. It's an Algebra 1 concept, and you did learn it in Algebra 1. So what you want to do there is you want to get all the variables on one side. So the z squared and the 12z stay on that left side. And you're going to add the 48 back to the other side. And I know we took it back to that side. Now we're taking it back. So we're going to do that. But what I'm going to do is I'm going to leave a little blank space on each side. Because what I'm going to do is I'm going to add something to each side. And so when you think of a quadratic equation, ax squared plus bx plus c, the b term in this quadratic equation is 12. You're going to take that 12 and you're going to divide it by 2. And that'll give you 6. And then you're going to square it. So you're always going to do that in completing the square. So you're going to take 12, you're going to divide by 2 and get 6, and then you're going to square it. And that's 36. But what you add to one side of an equation, you must add to
The other side.
to keep the equation balanced. Otherwise, you're changing the equation. And then what happens here is z squared plus 12z plus 36 is factorable. There are two numbers to multiply to 36 and add to 12. But I'm just going to tell you a little secret. When you complete the square, you've made it a perfect square. So the factor is going to automatically be z plus or minus half of that b term quantity squared. How do I know if it's plus or minus? Well, if b is positive, it's plus, and if b is negative, it's minus. But if you don't remember that, then you can just factor z squared plus 12z plus 36 and recognize you have two factors that are identical, so we can write it as z plus 6 squared. And then to solve this, Mick's going to tell us where to go from here.
So now we can take the square root of both sides. So we're going to take the square root of z plus 6 quantity squared, which taking the square root and squaring are inverse operations. So they cancel each other out, and we end up with z plus 6 equals, here's something to just be careful that we remember. When we take the square root of 84, we need to put our plus or minus. So we're going to have plus or minus square root of 84, but 84 contains a perfect square factor, so we have to simplify by factoring out the 4. The square root of 4 is 2, so we're going to write 2 outside of the radical after we've taken the square root times the square root of 21.
And for this problem, once you isolate x, you could leave your answer like that, but if you just plug that into your calculator, you could get the decimal answer. And realizing if you subtract -6 minus any number is negative. And do we want a negative answer?
No.
No. So we're just going to do the plus portion. And so if you left your answer -6 plus 2 root 21, that would probably be fine if we asked for the exact answer. Otherwise, you could get the decimal. And I actually got both decimals here, but recognizing that the negative decimal is not an option.
And just to point out a couple of things. One is when we complete the square, we only want to do that if the coefficient of the z squared term is 1.
Oh, good for pointing that out.
Yeah,
Thank you.
because if we have one where the coefficient of z squared is not 1, it's much easier just to use the quadratic formula.
Yes.
And then just one other side little note, somehow we changed from z to x, but that is the answer for z.
Oh, yeah. That was my fault.
No big deal.
Right, but I changed it
We
to
all
X,
do
but
that.
we know it's Z.
Yeah, it's z. Okay, folks?
All right, let's move on. Anything else, Mick?
I was just going to add that you could always use the quadratic equation to solve.
Quadratic formula?
Sorry, yeah, the quadratic formula. So that is an option on this problem, or even the problem we saw earlier with factoring. It's longer, so this can be more efficient, but it's always correct to use a quadratic formula.
Awesome. All right, here we go. So we talked about an external section and the entire thing when it's secant. And then I also mentioned that when it's tangent, the external and the entire thing is the same thing. So when you multiply two numbers that are the exact same together, it's the same thing as squaring the number. So EA times EA is the same as EA squared. So as you can see here, that's the idea that I just explained.
And the other part is the same as what we were just doing, the external segment times the entire secant segment.
Yep. Great. So we're going to do some problems. Anything you want to add here, Mick? Okay. All right. So we're going to do some problems here. So on the first example, I'll do the first example. And so on the first example, Wx is the external and the entire thing. So x times x is x squared. So you got x squared equals 12 times 12 plus 15. And that's 27.
And if you happen to know this, the square root of x squared is 18.
18.
One shortcut you can take if you're not good at remembering square roots is you could factor down the 27 and the 12 more in order to try to write it in simplest form, and you'll discover that it ends up being 18. But if you remember it, it's easier.
Yes, exactly. And you could do something like the square root of 27 times the square root of 12. And if you simplify the square root of 27, I think at this point you guys are pretty good. It's going to be 3 root 3. And the square root of 12 is going to be 2 root 3. And then when you so if you were doing this without a calculator, this might be a good thing to do. Because then you don't have to multiply these big numbers together. And so the square root of 3 times the square root of 3 is just 3. So you're going to get 3 times 3 times 2, which gives you 18. So that's another option. Okay? All right, we're going to move on.
Okay, you can see on this next problem that we've already highlighted the external part of a secant, which goes from W to U. And the external part is just 1, but the whole thing has 2 radii plus the one on the outside. So you can write that expression as 2r plus 1, because you're adding all 3 of those together to get your entire secant segment. Okay, and you're only multiplying it by the external part, which is just a 1, so that's easy. But the next one is a tangent, so the entire segment and the external part are identical, so it's just going to be 3 squared, 3 times 3. So here we are, just simplifying it and solving. Pretty easy to do, a little bit of algebra. There you go.
All right. And I believe that completes our lesson. Yes, it is. We are done with this lesson. Thanks for tuning in. And like I said, the spreadsheet, the links on School Loop, and I also put the link in the email that we sent you at the beginning of this experience that we're having. So we'll see you next time. Thank you.